Hello and welcome to Principles of Mathematics lesson number 16. In this lesson, we're going to study the set of rational numbers. We'll be looking at different representations for rational numbers, also at equal fractions, equivalent fractions, and the simplest form of fractions. We'll look at ordering of rational numbers and also the denseness property of rational numbers. Simply put, rational numbers are basically the set of the familiar fractions that we know about. When we write a fraction, we know that the top part is called the numerator, the bottom part is called the denominator, and we put a bar in between. Now, the set of rational numbers is then possible to define as we use the letter Q, and that stands for all numbers of the form m over n such that m and n both belong to the set of integers, and of course we need the stipulation that n should not be 0, because as you know we cannot divide by 0, so 0 cannot be the denominator of any fraction. Whereas we can take something like the set of natural numbers that we've seen before and use the roster method to list all the elements like 1, 2, 3, etc., right? Or the set of whole numbers, which we know is the set containing 0, 1, 2, 3, and then on forever. Or the set of integers, which we know we can represent in this way. We start with an ellipsis, then list a few negative numbers, then 0, then 1, 2, 3, and then on forever, right? So all the whole numbers and their opposites, comprise the set of integers. With the set of rational numbers, we can't quite use the roster method because there's no simple way to represent all fractions in such a way that we could just list a few and then put an ellipsis, indicating that the pattern goes on forever. We don't have such a pattern. So we have to use the other set notation, the set builder notation, where we're basically giving instructions for how to build the set rather than listing all the elements of the set. When it comes to the set of integers, there is a nice, more compact form of it. We can put 0, plus or minus 1, plus or minus 2, plus or minus 3, and then put the ellipsis. Now, this is the same as that. It's just a more compact form of it. But we don't have a similar notation for Q. There are many instances in life where the use of fractions comes in. For example, whenever we have a multiplication problem, we usually end up using fractions at some point whenever we're dealing with parts of a whole, etc. Like the solution to the simple equation 2x equals 3. So if you start with 2x equals 3, you know that all you have to do is to isolate x, is to divide both sides by 2. Then the 2's here cancel out, we get x equals 3/2, right? So notice that the solution of this equation does not belong to any of the sets we've studied, the natural numbers, whole numbers, or integers. So this is where the set of rational numbers comes in, for instance. Or we can talk about one person receiving 1/2 of another person's salary each month for alimony. There again, we need to use a fraction. Or the ratio, for example, the ratio of Republicans to Democrats in the Senate may be 3 to 5 at a given time, right? So this would be another scenario where we would use a fraction. Probability, for example, when you toss a fair coin, the probability of getting heads is 1/2, and that's also a place where we would need to utilize fractions. There are different models for representing a fraction. Here we're looking at an area model where in this figure 1/3 of the figure is shaded, so the shaded part would represent 1/3 here, in this number line scenario, 2/3 of the distance between 0 and 1 is shaded, so that would represent 2/3. In this set model, we have 5 elements in this set, and 3 of them are shaded, so that would represent the number 3/5. To understand the meaning of any fraction a over b, where a and b are whole numbers and b is not 0, this is of course if we're only limiting ourselves to non-zero non-negative fractions. So when we're dealing with non-negative fractions, then we need to understand the whole in question, the number b of equal sized parts into which we have divided that whole, and the number a of the parts of the whole that are selected once that partition has been made. We generally encounter 2 types of fractions, what we call a proper fraction and an improper fraction. A proper fraction is simply a fraction where the numerator is strictly less than the denominator. Okay, again here we're dealing with non-negative fractions because we're assuming that 0 is less than or equal to a less than b. Now the possibility of 0 does exist, if the fraction could be 0, but we call a fraction proper whenever the numerator is strictly less than the denominator, such as in this case, right? Now, here, of course, we're given an example of a proper fraction, but in this case, we've used negative. So this is actually contradicting this, the fact that 0 is less than or equal to a, but it's not incorrect. It's just that this stipulation shouldn't have been made in this diagram. Improper fractions are fractions where the numerator is larger than or equal to the denominator. So 8/5 and -3/2 would be considered improper fractions. Notice also this is one that some students missed. 5/5 would also be considered improper because we cannot have the denominator and numerator even be equal in the case of proper fractions. So 5/5 would also be considered an improper fraction. Here we've represented these numbers that you see written in red on a number line. So here we have, for example, -1, -3/2, -7/4, -1/4, 0. Of course, notice you can also write 0 as 0/1, right? So that's also considered to be a fraction. Or 1 can be written as 1/1, 2 can be written as 2/1. So this gives us an interesting indication that it appears that we can do that to all integers, right? We can take any integers and put a denominator of 1 under it. Therefore, this is what makes the entire set of integers a subset of the set of rational numbers, right? And of course, notice we can also do that to natural numbers and whole numbers, right? So this is why we have this particular relationship. The set of natural numbers is a subset of the set of whole numbers, which is a subset of the set of integers, which is itself a subset of the set of rational numbers. And of course, all of them live on the number line, so they're all also a subset of the set of real numbers. So we have this nested relationship between these sets. Equivalent or equal fractions are basically fractions that may look different, but once simplified according to rules that we're going to learn, we will see that they actually represent the same quantity. So one way of saying that is that they represent the same point on a number line, okay? So notice this is a nice visual representation of the fact that 1/3, 2/6, and 4/12 all represent the same quantity. And basically, if you simplify both of these other ones, 2/6 and 4/12, you'll also come up with the simplest one, which is 1/3, right? Now, this is in simplest form because the numerator and denominator don't have any common factors other than 1, right? So they're relatively prime. Whereas notice these two, for instance, are not relatively prime because they share a common factor of 2, right? Other than a factor other than 1. Same with 4 and 12. Okay, they would not be relatively prime because their GCD is 4, which is not 1. Remember, two numbers are relatively prime if and only if their GCD, or greatest common divisor, is 1. Here's another way we represent fractions to younger students. Here we have 1 whole here, then we're looking at a half here, and we also notice that a half can also be represented using 3/6, right? Or 6 of these 1/12 pieces, right? So there's an equivalence there. And 1/3, for example, notice that could be represented using 2 of these 6 or 4 of these 1/12 pieces, right? All right, next we have what is called the fundamental law of fractions, which basically says if you have a fraction a over b and n is any non-zero whole number, then we can multiply n by the numerator and the denominator, and we end up with the exact same fraction as far as value is concerned. That is if you look at this statement from left to right. Now, if I write it in the other direction, if I write an over bn equals a over b, then this is considered the cancellation property. Because basically what we're saying is that here we can, if we're given an over bn, we can cancel out the n's, right? And we end up with what? With a over b, right? So in essence, we're dividing the numerator and the denominator of this one by n, right? And getting rid of the n's, leaving 1's in their place. So we end up with a times 1, because each will leave a 1 once we cancel it. So we get a times 1, which is a, b times 1, which is b. So when you look at the fundamental law of fractions in reverse, you get the cancellation property. Very important property, because this is basically the property that we use to simplify fractions. To the point, of course, where the numerator and denominator become relatively prime and hence cannot be simplified or reduced any further. Okay, let's go ahead and take a look at a quick application of the fundamental law of fractions. Which basically says you can take any fraction and multiply the numerator and the denominator by a fixed number and leave the value of the fraction unchanged. So notice that here all I need to figure out is what I have to multiply 42 by to get 210. Then I'll take that number and also multiply it by 12, and I'll find out what x is. So the first thing we'll do is find out what it is that you need to multiply 42 by to get 210. And of course, if you think about it, 40 times 5 is 200, and 2 times 5 is 10. So that's basically going to be 5. If the number that we need to multiply 42 by to get 210 is 5, so which means this number here is 42 times 5. So this value of x is going to be none other than 12 times 5, because what we're doing is we're multiplying the numerator and denominator of a fraction by the same number as is allowed by the fundamental law of fractions. And this, of course, results in x being 12 times 5, which is 60. So basically what we're asserting is the fact that the ratio of 12 to 42 is the same as the ratio of 60 to 210. We're going to be studying equations of this type in much more depth later. Uh, Equations which state the equality of two ratios are called proportions, and they're extremely important equations. We'll be revisiting them and we'll learn how to solve them in a much more efficient way so that we can handle situations where the scenario is not so simple as just multiplying by a whole number. Maybe we have to multiply 42 by some complex fraction to be able to get to the number over here on this side. So we'll be able to handle all that once we learn more about proportions and the principle of cross multiplication. So make sure you can handle a simple problem like this before we proceed. All right, so as we mentioned already, a rational number a over b is in simplest form or lowest form if and only if the GCD of the two numbers a and b is 1. That is, if a and b have no common factors greater than 1. Remember that we can also say in that case that a and b are relatively prime. All right, so here we have some fractions that we want to simplify and put into simplest form if not already there. All right, so we noticed that in the first one, we have two numbers, 28 and 42. One very efficient way of coming up with the cross cancellations that are necessary is to go ahead and find the prime factorization of each really quickly. So we take 28 and we know that 2 goes into it 14 times, 2 again 7 times, and 7 goes once, right? So for 42 a squared, just 42, we go ahead and break it down and we get 2 gives us 21, 3 gives us 7, and 7 gives us 1. So we notice that we can write 28 as 2 times 2 times 7 times ab squared, and we can write 42 as 2 times 3 times 7 times a squared b squared. Now we can cross cancel the 2's, for example, the 1, 2 on the top with 1, 2 on the bottom, right, using the cancellation property, and we can cancel out the 7's, 1 7 on top with 1 7 on the bottom. Notice the b squares completely cancel out. Of course, notice they all leave 1's, right? We normally don't write the 1's, but you could if you like, okay? And notice that a and a squared cancel out, leaving an a on the bottom, right? Because notice on the top you have an a, on the bottom you have a times a, so when you cancel like that, you're only left with an a on the bottom, right? So be careful when you do that. So you get a. All right, and now we just go ahead and write what's left. So on the top, we notice that all we have left is a 2. And on the bottom, if you notice, we have 3 times a, so 3a. So there is the simplest form of this fraction right here. Okay, next we have this one. Now, there's not much factoring I can do up there, but I noticed down here I have a common factor of 3, right? So we can go ahead and factor that out. So we take out the 3, that leaves us a plus b, right? Remember, we're applying the distributive property in reverse, right? So now I notice that, look, I have a plus b here, and I have the square of a plus b up there. So this is the scenario. You have a plus b times a plus b on the top, and you have a plus b on the bottom. Notice we cannot cancel just the a part of a plus b or the b part. You never do that, right? You never cancel a part of something that's attached to something else, right? But I can cancel the whole a plus b here with the whole a plus b down there, because then I'm canceling out factors. You can always cross cancel factors, but you can't cross cancel terms, right? So I notice this cancels with this, leaving me 1a plus b on the top, right? So we end up with just a plus b on the top and only 3 on the bottom. All right, I hope that you are following our usual practice of pausing the video and trying these on your own before you're proceeding to watch how I do them, because that's how you learn mathematics, by being involved, okay? So now right here, we've done something similar to this before. Remember, here these two have a common factor of x, so we can take it out, and that leaves us x plus 1, right? Try it out, multiply it out, and you should get this. X times x is x squared, x times 1 is x, right? So we did it correctly. And we have x plus 1 down here. Again, remember, you can't cross cancel, for example, this x with that x, because that's a factor, but this is a term in a sum, right? You never do that, remember that. But I can I can cancel all of this x plus 1 with all of that x plus 1, and that's perfectly fine. So we do that, and we get equals x. So there are the simplified versions of those fractions. Make sure you can handle these before we continue. All right, here we have another example where we're going to simplify these fractions if possible. Now, in this first one, notice these two terms do not have a factor common other than 1, right? So there's no factoring possible, and there's not much we can do down here, right? And this goes back to what I was telling you in the previous problem. You would never cancel those 3's, right? So notice that we would basically be left with no option here to say that this cannot be simplified any further. In other words, it's already as simple as it's going to get. So let's go ahead and see why you shouldn't do that. Okay, we're going to look at an example. Remember, all you need to know in order to avoid doing something is one example where that fails, right? We call it a counter example. So let's take a look at that and see why you should never cross cancel terms with anything else. So here's a term, we never cancel it with that factor. Here's why. Suppose we look at 5 plus 10 over 5. A very simple example, right? If a student incorrectly, and remember, don't do what I'm about to do, I'm just telling you what you shouldn't do. But if you were to incorrectly do that, that would leave a 1, so this would end up being what? 11, right? This is wrong, okay? Of course, the correct answer per the order of operations is to go ahead and add the 10 and the 5 to get 15 over 5. Now it's perfectly safe to go ahead and cross cancel in this manner, and you're left with 3. So notice that the correct answer is 3, but if you were to do this very incorrect operation of canceling this term that's attached to another term with a free factor down here, you would end up with that erroneous answer. So please make sure to never cross cancel. And that goes with letters and variables too, right? So here this x squared should not be canceled with that x squared, because this is a term attached to another term. This is a free factor. So whether you're canceling a term with a factor or with another term, so even if I have, like, say, a plus b over a minus b, now Both of these are terms attached to other terms, so we should definitely not cancel the a's, and we should definitely not cancel the b's. So here again, this would be as simple as it's going to get. You would not do any changes there. Not the case with this other one, right? Take a look at this, try it on your own, then come back, see if we agree, okay? Now, with this one, if you notice, these two terms do have a common factor of 3, so you should be able to factor it out. What would that leave us, right? When I take out a 3, that would leave me a 1 for the first term, and it would leave me x squared from the second term, right? In case you're confused, remember, you can always think of that 3 as 3 times 1, right? Plus 3 times x squared. So when you factor out the 3, it does leave you that invisible 1, which we usually don't see, plus x squared. So in here, it would leave you 1. In this one, it would leave you x squared. If you don't write that 1, you're going to miss the problem, because when you multiply it back in, you would only have 3 and x squared, so you would get 3x squared. But when you multiply this out, 3 times 1 is 3, 3 times x squared is 3x squared, which means we factored correctly, because when we multiply it back out, we get the original expression. Down here, we have 3x squared. So now, this 3 is a factor. It's being multiplied by some other expression, right? So it's perfectly, and so is this 3, right? That's a factor being multiplied by x squared. So these are now free factors. They can be cross-canceled, right? So we're left with what? We're left with 1 plus x squared on the top, and we're left with x squared on the bottom there, okay? So that would be the simplified version of that problem. All right, so how would we show that two fractions are basically equal or equivalent? Well, in the case of simple numbers involved, right, all we would do is, one way of doing it would be to show that their reduced or most simplified form are the same. Look, start with 12 over 42 and reduce it, right? Now we know that, again, you can just cross-cancel in the traditional way, or you can use prime factorization, either one. Just to practice prime factorization, let me show you. 12, 2 goes into 12 6 times, 2 goes into 6 3 times, and 3 goes into 3 once. So there's the prime factorization of 12. It gives me 2 times 2 times 3. 42 factors out using 2 gives us 21, 3 gives us 7, and 7 gives us 1, right? So notice I can rewrite the numerator as 2 times 2 times 3, and the denominator as 2 times 3 times 7, right? And you can see that here, 2 times 3. So the beauty of this method is that the prime factorization is on the left, and since we're always dividing by the smallest prime that goes into the number on the right, everything is nicely ordered for you, right? So now we notice that we can cancel one of the 2's on the top with one of the 2's on the bottom, and 1 3 on the top with 1 3 on the bottom, and we're left with 2 7ths, right? Now, if I do the same thing with 10 over 35, this is really simple. I'm going to skip this business because you know 10 is just 2 times 5. You can, of course, do this if you need it for yourself. And 35 is 5 times 7, right? So I can go ahead and cancel out the 5's, and we get what? 2 7ths. So we just showed that both of them reduce to the exact same fraction. So we can say, therefore, 12 over 42 equals 10 over 35. Okay, so that's one way of showing two fractions are equal. Another way to show that two fractions are equal is to show that to rewrite both of them using the same denominator. Now, at first we'll do it using the least common denominator because it'll give us some practice with that too. So for that, let me quickly do the factorizations of 42 and 35 again. 42, 2, 21, 3, 7, 7, 1. For 35, we have 5, 7, 7, 1. So 42 is 2 times 3 times 7, and 35 is 5 times 7. You know that for the least common denominator, which is basically the least common multiple of the denominators, right? We call it the LCD, right? Remember, it's just the LCM of all the denominators. So we're going to need the highest power of each factor that we see in all factorizations, right? So we need a 2, we need a 3, we need a 5, and we need a 7. We're going to multiply all that out, and that will give us the least common denominator. Now, 2 times 5, we're going to use compatible numbers. 2 times 5 is 10. 3 times 7 is 21. So we can see that the LCD is 210. So I'm going to go ahead and write the first number as a denominator as 42 times. Now you can actually see what 210 divided by 42 will be by looking at this prime factorization, right? Look, I know that 2 times 3 times 7 is the 42 part, so I need a 5, right? So times 5, that means I would have to do the same to the numerator and multiply it by 5. Now for 35, look at this prime factorization for 210. What part of it is 35? This part right here. So that means I need a 6 to get me to 210. So times 6, and I would have to do the same on the top. So notice that I end up with 60 over 210 for this fraction, and I end up with 60 over, what's 35 times 6? Well, we know what it is. It's right here. It's 210, of course. So we get 60 over 210 over there as well. And there we have shown that these two fractions are equal because we've been able to write them using the same denominator, and we ended up with the exact same numerator. So clearly the two fractions are the same. Now, given that we have calculators readily available to us, we don't really need to go for the least common denominator. If I just want to quickly show that these fractions are the same, I will just take a common denominator and show that they can both be written using the same common denominator, right? And of course, the easiest common denominator you can get is just multiplying the two denominators. So I'm going to take 42, multiply it by 35, and I'll take the 35 here and also multiply it by 42. So in the first fraction, the denominator is being multiplied by 35, so we're going to do the same to the numerator to keep the fractions the same. And for this denominator, it was multiplied by 42, so the numerator also needs to be multiplied by 42. So now we just go to our calculator and we go ahead and figure out what 12 times 35 is. And we get 420. So the first fraction is now equivalent to 420 over, sorry, the other way. Yeah, 420, no, we were right. 420 over. Now we will do 42 times 35. That's 1470. On the other side, of course, 10 times 42 is also 420, so we get 420 over 1470. And there we have shown that the two fractions are equal by writing them using a common denominator. And of course, the easiest common denominator, just multiply the two denominators, right? Now, there it is. There's another way we could use to show equivalence. All right, now we get to the fastest and most elegant way of showing that two fractions are equal. And that's by observing the fact that two fractions a over b and c over d, with of course b and d not being zero, not just d, are equal if and only if AD is equal to BC, meaning A times D equals B times C. Let's see why that's true. This is basically called the principle of cross multiplication. So we start with A over B. So here's a rough proof, okay? So if A over B equals C over D, notice that the least common denominator here would be BD, right? So if we multiply both sides by that LCD, which we can do, right? We already know that as a property of equality. If A equals B, then A times C equals B times C, right? Multiply both sides of the equation by the same number and you don't alter the truth of the equation. Now, if you notice, we can go ahead and look at these as fractions like that, so we can cross cancel anywhere from a denominator to a numerator, as long as the only operations going on are multiplication on top, multiplication on the bottom. We can do that. So notice that these b's would cancel out, and on this side the d's would cancel out, and what would be left with? We would be left with AD equals CB, which is the same as BC. Okay, again, this is also known as the principle of cross multiplication, because you're multiplying across like this, right? AD equals BC, okay? So the fastest way to check see if two fractions are equal is cross multiply and see if these are called cross products, AD and BC. When you have a proportion like that, those are called cross products. Make sure the cross products are equal. Let's try that with the fraction we've been looking at, or fractions I should say. 12 over 42. We want to know if that's equal to 10 over 35. So we quickly calculate the cross products. We multiply 12 times 35. That's one cross product. The other is 42 times 10, right? Now we know this one is 420, and we've already seen, so we put a question mark there too, we're still checking. So we've already seen that 12 times 35 is also 420. So on this side we also have 420. So this checks out. So this tells us what? That these two fractions are equal. So a very nice, quick, elegant way of proving the equality of two fractions. All right, so as long as the denominator here is positive, we can establish this fact for inequalities as well. We can say A over B is greater than C over B if and only if A is greater than C. So if we're comparing two fractions with the same denominator, as long as that denominator is positive, then all we have to do is look at the numerators. If this numerator is greater than that numerator, then this fraction is going to be greater than that fraction. For example, if we have 3/5 and 2/5, obviously, to compare those, all we need to do, because these 5s are the same and they're positive, all we got to do is look at the 3 and 2. And of course 3 is greater than 2. That tells me this fraction is going to be greater than that fraction. Now if we're dealing with two different denominators, as long as they're positive, right, we can use the cross multiplication trick with saying this: if A over B is greater than C over D, if and only if the cross product AD is greater than the cross product BC. Okay, So here we have two fractions, you can see, and you can see that 11/12 is clearly larger than 4/5, right? So we can quickly verify this if we can show that the cross product, remember you have to go from the top left to the bottom right, this cross product, be careful with that. So we can see that 55 is greater than 48, so therefore we've established that 11/12 is definitely greater than what? 4/5. So a nice quick way to see if an inequality holds in this way. Okay, next we want to look at the denseness of rational numbers. So that means, like, if you're on the number line, right, how close are rational numbers on this number line, right? We know, like, for example, whole numbers and integers, there's a gap between them, right? From 0 to 1, there's a gap, from 1 to 2, etc. And that's true about any two distinct integers or whole numbers or natural numbers. Not so when it comes to rational numbers. They're very densely packed on the set of real numbers or on the number line. In fact, if you have any two rational numbers, there's always the possibility of finding another one between them, no matter how close you think they are, okay? And let's take a look at that real quickly with an example. All right, let's say that we want to find two fractions between 7/18 and 1/2. One real easy way to do that is to go ahead and write both of these fractions with the same denominator. Now, in this case, we can see that the least common multiple of 2 and 18 is just 18. So if I just take this other fraction, the 1/2, and multiply the denominator by 9, which means, of course, I have to do the same thing to the numerator, notice I end up with 7/18 and 9/18. Now, obviously, it's very easy for me to get a fraction between these two by just looking at 8/18, right? But I want two fractions in between. So there's a really nice trick using the fundamental law of fractions, which is I know I can multiply both of these fractions by the same number again. So for example, I can multiply the 18 by 2 and do the same thing to 7. And I'll do the same thing on the other one because I want to keep my denominators the same, right? So notice now I get 14/36 and 18/36, right? So now I know that 14/36 has the exact same actual value as 7/18, and I know 1/2 and 18/36 are also equal. So I'm still working with the same two fractions, right? But now I can easily find two fractions in between. So for example, I know I can get 15/36 and say 16/36. And when you want to present your answers, you usually want to go ahead and give the simplest form. So I noticed that, for example, 3 goes into 15 5 times, and it goes into 36 12 times. And with this other fraction here, I know that 4 goes into 16 4 times, and it goes into 36 9 times, right? So I can answer 5/12 and 4/9, for example. Notice there are other possibilities, right? But just to give you another method for knowing why no matter how close two fractions are together, you can get another fraction in between them. do the following. Notice that if you have a over b and c over d, right, you can always find the midpoint of those two points, right, on the number line by just adding them and dividing by 2. But remember, dividing by 2 is the same as multiplying by a half. So I can just take 1/2 times the sum of those, and I end up with what? I end up with another fraction that's going to be in between those two fractions. So there is one quick way to prove that given any two fractions, you can come up with at least one other fraction in between. And notice that you can do that again, right? With the first number and the 1/2 way that you found, you get another 1/2 way between. You can do it again. And notice in this way, you can actually fit what? Infinitely many fractions between any two fractions. All right, the set of real numbers is like a wonderland, and the more you learn about it, the more fascinating it gets. Here is another really quick way to get a rational number between two other rational numbers, again, as long as the denominators are positive. It turns out that if a over b is less than c over d, then the fraction a plus c over b plus d, which is basically the sum of the numerators for the numerator and the sum of the denominators for the denominator, is going to fall between a over b and c over d. Now, the proof of this fact is not that difficult, and I think it would be great practice for you. But I'll give you a hint. Basically, start with your original inequality. You know that from a previous fact that we've discussed, this is going to make AD less than BC. Now, you would cleverly add the same quantity to both sides, which will eventually lead to first this inequality, and then you would start over and add a different quantity to both sides, and that would lead to this inequality. Then you can safely say that you've established the inequalities, this compound inequality. So basically, we are going to be able to use it to quickly come up with a fraction between two other fractions. All right, that brings us to the end of the lesson proper. So at this point, per our usual practice, we'll go ahead and look at some of the homework problems. All right, so here we're looking at pairs of fractions, and we want to know which one is larger, greater than the other, or whether they're equal. So of course, you're looking at 5, 6, and 7, 8. Remember that we can look at the cross products, and we see that 40 is less than 42, so that's going to make 5, 6 less than 7, 8. And this works even with negative numbers, right? Notice that negative 21, for instance, is actually less than negative 16, right? So this is also going to make the first fraction less than the second fraction. So keep in mind, we're using the fact that a over b is less than c over d if and only if AD is less than BC, as long as B and D are positive, okay? So there you can do it that way, or you can of course also write both of the fractions with the same denominator, and then you only have to compare the numerators, right? If the denominators are the same, all you need to look at are the numerators. So there's another way. Try both ways to convince yourself, okay? All right, this problem deals with what I was telling you about all integers also being rational numbers, because remember, the set of rational numbers Q is the set of all fractions of the form m over n, such that m and n belong to the set of integers and n is not equal to 0. So if you take the set of integers which is composed of 0, 1, 2, 3. Actually, let's start with the negatives. That's better. So dot 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 -3, -2, -1, 0, 1, 2, 3, etc. Notice that you can simply take each of them and throw a 1 underneath, and you've satisfied the requirement for being a rational number, which is you have fractions of the form m over n where both the numerator and the denominator are integers, and the denominator is not 0 because obviously they're all ones, right? So in this way we show that the set of integers is a subset of the set of rational numbers, and it is a proper subset. And of course, if you're talking about the general integer n, then all you have to do is write it as n over 1 to show that it can be written as a fraction. Okay, so here we're asked to basically simplify these fractions and find out what expression they'll be equivalent to. So if you notice, for the first one, we've already discussed this. These two here are terms in a sum. They cannot be cross-canceled, so neither one of them. So this is already as simple as it's going to get, right? So make sure you understand that. But these ones are kind of interesting, so I wanted to look at them with you. Notice that on the top here, we have 2 to the 5 and 2 to the 4. Notice that when you're dealing with the same number for the base, then powers with lower exponent values do go into powers with higher exponent values. For example, notice that 2 to the 5 is divisible by 2 to the 4. That's simple because you know 2 to the 5 is 2 times 2 times 2 times 2, and 2 to the 4 is 2 times 2 times 2 times 2. Notice 4 of those factors on the top will cancel 4 on the bottom, and you're left with 1 more on the top. So we say 2 to the 4 goes into 2 to the 5 2 times, right? Now, if we had, for example, 2 to the 5 over 2 squared, right? Then, of course, you know that you could also quickly, instead of having to go through all that, use the quotient rule to realize that's 2 to the power of 5 minus 2, which is 2 cubed. So we say 2 squared goes into 2 to the 5 2 cubed times, right? Or 8 times. So keep that in mind as I proceed with factoring these. Notice that these two do have a common factor, so it's 2 to the 4. When I take that out, that leaves me a 2 from the first term plus, of course, just a 1 from the second term, right? Now, multiply it out. 2 to the 4 times 2, that's 2 to the 1. So using the product rule, we get 2 to the 4 plus 1, which is 2 to the 5. Plus, and 2 to the 4 times 1 is 2 to the 4. So we have correctly factored the top. Now we're going to do the same on the bottom. Notice that 2 cubed does go into 2 to the 6, so we have a common factor of 2 cubed. Now that leaves us 1 plus, so what is 2 to the 6 divided by 2 cubed? That's 2 to the 6 minus 3, or 2 cubed, right? So that part leaves us 2 cubed. So we have 2 to the 4 over 2 cubed, which we can now cross cancel. Because notice now they're factors. We couldn't have canceled them before because they were terms in sums, right? But now this is a free factor, that's a free factor. We can cross cancel them. That leaves you, of course, a 2 on the top. So I have 2 times, what is 2 plus 1? That's 3, right? And down below, we just have this expression. So 1 plus 8, right? Remember, 2 cubed is 8. So we get 9. So now, notice that the 3 and the 9 can cross cancel, leaving you a 3 on the bottom. So that expression becomes equivalent to what? 2/3. So that's how you would approach that. All right, so this I'm going to leave for you, but it's done very similar to what we just did over here. So make sure you try it. I'll give you a hint. Your answer should come out to be 3. Okay? So work it out. Make sure you get the answer 3. All right, so here we want to find x in each of these. Notice that the 5 here has been multiplied by 4, so we're going to multiply 4 by 4 to get what? 16. Now for this one, and this is why I wanted to show you this problem, notice that we have 4 over x equals 4x over x squared. We know that we can cross cancel 1x with 1x down here, leaving us another x, right? So now the equation becomes 4 over x equals 4 over x. Well, obviously 4 over any number equals 4 over that same number, right? So this is going to be true for all integers, except, of course, we know that x shouldn't be what? X shouldn't be 0. So this x is any integer other than 0. For example, notice 4 over 2 equals 4 over 2. Do you agree? 4 over 5 equals 4 over 5, etc. So any integer can work. 4 over negative 3 is the same as 4 over negative 3. The only one you need to avoid is 0. As long as x is not 0, this equation, which is known as an identity, is going to be true. All right, so here they want us to explain why 20 cents is 1/5 of a dollar, but 12 minutes is 1/5 of an hour. Why should these 1/5 not be equal? Because, of course, we have different contexts. We're different wholes that we're dealing with, right? Here we're dealing with money, so a dollar turns out to be 100 cents, right? So 20 over 100 will give us 1/5 there. But here we're dealing with an hour, a completely different context, which is equal to 60 minutes. And 12 minutes over 60 minutes, of course, the minutes cancel out, you get 1/5. So we're dealing with different contexts, therefore different wholes, right? All right, so here we have one student that writes 15 over 53 is less than 1/3 because 3 times 15 is less than 53 times 1. So, of course, as we know from the lecture, this student is correct. Another student writes, hey, 15 over 53, we can cancel out the 5, so it's 1/3. So what's the problem here? Well, this student obviously does not understand the concept of cross-canceling. You can never cross-cancel like that because we don't cancel based on the digits that are there. We cancel based on whether these two numbers have a common factor and then dividing off that common factor. So there's a misunderstanding about the process of cancellation here. All right, so here we have two classes that were given the same test. In class A, 18 out of 30 students passed, and in class B, 24 out of 40 students passed. One of the students in class B claimed that the classes did equally well. How could you explain the student's reasoning? Well, it seems like the student was pretty good in math because they basically figured out that 18 out of 30 is the same as, notice 6 goes into both 18 and 30, so 18 divided by 6 is 3, and 30 divided by 6 is 5. Also, if we look at 24 out of 40, we know that 8 goes into 24 3 times and 8 goes into 40 5 times. So in both cases, 3/5 of the students passed. So therefore, yes, they did equally well. Okay? All right, so notice that here we want to rank these fractions that are we have here based on the images, and you can see the smallest from the smallest to the largest. So this would be the smallest, which we can see represents 1/2. Next in line we see is this figure. So as we can see, broken up into 8 equal pieces. 5 are shaded, so 5/8. This time this one comes next, which is if you notice is 4/6 or 2/3, same thing. And this of course has the largest amount of shading, which is 3 out of 4. So that's a nice problem as well. Okay, that should bring us to the end of this particular lesson. Take care of yourself, and we will see you for the next lesson.